So yeah, as I said, the technique that I want to use to discuss confinement is putting a quantitative theory in the anti-de Sitter space. Okay. So I want to start by giving some general reasons why this could be anti-de Sitter space or hyperbolic geometry could be an interesting background to set up some QT problem. So let's start from the basics. If I'm going too slow, you can tell me that you want to know this, and we can go a little bit faster. So I'm going to just consider a Euclidean version in my classes. So let's just draw some pictures. A very familiar set of coordinates with the Poincare coordinates. Okay, which is some flat slicing, meaning that we are just polymating this positive z, and then at each z we have a flat space. And this is the way the geometry looks. Okay, so you have this L is the radius. Okay, meaning that if you compute the curvature, you have some negative number. And there is this z factor that emerges here, so it means that as we approach this boundary, we have more and more geometry, more and more space as we approach. Okay, so this boundary is an infinite distance from point inside. And the correct mathematical notion is that it is a conformal boundary, which means that the fact that you specify this geometry here doesn't tell you what is the metric on this asymptotic boundary. You should think about it as a boundary of infinite distance. And we don't fix a geometry here, we just fix formal structure, which means metric will scale. So okay, this was like just set up also some notation for the coordinates we're going to use. Another useful set of coordinates is with the spherical slicing instead of flat slicing. So the other set of coordinates, we view it as the inside of a ball. Okay, so this was like a half space basically. And now another set of coordinates is when we view it as the inside of a ball with some radial coordinate rho, some angular coordinate omega. You see, as I said before, since we only specify the conformal structure of the boundary, it's possible to go to another set of coordinates in which the boundary looks like a sphere instead of looking at a vector space. And in these coordinates, it looks like this. The cinch factor. And by this, I mean just the round metric. On okay, and so you see when you are close to the origin, and rho is much smaller than L, this looks like flat space in polar coordinates. And then when you go far away, instead you get this exponential growth. Okay. Now, having told you a bit briefly what is this Euclidean AdS, or known as hyperbolic space. Now, why on earth do we want to study quantitative theory in this background? You work about that. One thing that this space has is that this radius R L works a little bit like an asymptotic. So that may appear, even though it's not immediately obvious, because I told you before that it has infinite volume, there is more and more spaces across the boundary, but still this L tends to cut off the fluctuations. In what sense? All right. Perhaps the more practical way to phrase this is that if you study some propagators, let's say G of some massless particles. So I put, let's say, first here in the origin, and then the second one, some distance rho, phi 0, phi rho. So even if it is a massive field, when I study this propagator, I will find that they decay exponentially as rho becomes larger. And of course, this is possible exactly because we have this L, right? Like usually in flat space, what we're used to is the idea that coefficient. This idea is that if I have a massive particle, then I have an exponential decay when I take it to points far away, and with the power that is controlled by the mass, right? Here, even for massless particles, I have this type of exponential decay, which in this case will be controlled by the radius instead. Okay, so that's one practical way in which you can think about. Yes.
Is the mass something effect or using the coefficient?
So this is like specifically for massless particles. I'm saying it goes like this. Otherwise, for massive ones, I guess it depends a little bit on what is the relation between M and L. But I think if the mass is much bigger than this, it's going to be controlled by the mass. Otherwise, if it's all the same order,
Yeah,
so the words exists.
But can we write universal as just like scale and sometimes row?
Yeah, exactly. So, right. So, for those of you who are already familiar with this kind of stuff, this comes from the fact that basically the Laplacian has some eigenvalues that are controlled by 1 over L, is bounded from below, like it doesn't go all the way to 0. And because of the Laplacian, it's related to the scaling dimension of the operators. Did I answer? Okay, so this you might say, fine. So thanks to this, we have this kind of cutting off of fluctuations. But you might say, okay, but if I want to cut off fluctuations, I can just take my theory and put it in a box. Why do I have to do this esoteric thing of putting it in a hyperbolic space? Fair point. But compared to a box, it's also another nice thing that it's maximally symmetric. Okay. For this, you would say also a box. So if you want to be formal, you would say get things off the box as the torus t plus 1. But the torus t plus 1 doesn't have a lot of isometries, right? I break a lot of isometries because flat space, I have all my generators of translations and Euclidean notations, and they're all broken when I do this. This is like what is used on the lattice, no? You do periodic identification of directions.
What about a sphere? You don't get similar properties.
Yeah, that would be also my third point. So yes, at the moment, let me I'll mention that. So the isometries instead in an hyperbolic space, it's a big group, S to 1 d plus 1. So it's the same number of generations as flat space. Maybe I just one thing is that since we have a boundary, we universally think of our theories as in d plus 1 dimensions. So d reserved for the dimension of the boundary. Okay, so it's one of the most complicated things in this business is to remember what is d, and this is the dimension of the boundary. Okay, so you see, I introduce an ion regulator, but I introduce it in a very symmetrical way without breaking any generator. So that's nice. And again, okay, it was already asked this question. You could say, you could read thoughts on the sphere. Why don't you take your theory and place it inside of a sphere? Okay, you for sure you will cut off by fluctuations. There is no way to go. There is no. And you will also have the isometry will be SO d plus 2, but it's still the same number of isometries. Well, the disadvantage of the sphere is that, so another, in a positive way, another nice thing of the hyperbolic geometry is that we have infinite volume. And we can define asymptotic observables. Okay. But yes, the sphere is nice, but the sphere will never be able to discuss stuff like spontaneously breaking or anything that even resembles a little bit scattering amplitude, right? If I study my theory here, I don't have an infinity space where I can send my particles from and let them go to. So it's a bit more boring. That I can just compute things which are analog of correlators, okay? But I can do stuff which is more similar to scattering. Instead, in this hyperbolic geometry, I even get to discuss things at infinity. Okay, that's very nice. So what do I mean by asymptotic observables? It's a bit of a sweet spot because we both have an ion regulator, but we have infinite volume. Okay, so these two things are not so easy to come by. So asymptotic observables are correlators of local operators inserted at the boundary. Okay. Adesso lasciamo calcolare. That just means that we will have the possibility to compute correlation functions just inside this conformal boundary. And of course, I guess everybody here is familiar with this from the DSCT. A very nice point is that this, yes?
Only local operators or also non-local operators?
Also non-local operators, but yeah, mostly I will focus on local ones in my lectures, but yes, you can also consider extended operators. So, a nice thing is that this isometry group acts on these correlation functions. So the correlators at the boundary, they are covariant under this SO1 equals 1. Okay. And the way this group acts on them is exactly like the conformal group acts on correlation functions in a conformal field theory. Okay. So this thing acts as individual conformal group of terms. So they are conformally covariant, these correlation functions. So what I want to say about these correlators? So as I already stressed, you can think of them as yes,
Sorry, it's important that so just on that, it's important that they are bound because like this they
yes.
are basically covariant the whole group, but if you put them like at finite distance from the origin, we will break this isometry depending on.
I mean, this group will act on some points inside.
Yeah,
but the way it acts on points inside is more similar to how translations and rotations act on a point in a correlation function activity. Right? So yeah, the whole thing must be, if you preserve the symmetry, the whole thing is covariant under this. I'm just saying that it's a little bit different how it acts on a point here compared to how it acts here. Here it acts like a Euclidean conformal group. Here it acts like an isometry of space that will move the point around, rotate the indices like the Poincare acts in flat space. Okay. Now, one thing, yes, I want to say that they are bit Euclidean analog of scattering amplitudes. For the theory in AdS. And there is one rich topic which I will not cover in my class, which is actually how to use these correlation functions, take the flat space limit, and recover from them scattering amplitudes. So there are well-studied subjects. How to recover amplitudes. Well, I would say that even though it's not studied, it's not completely well understood, not in all cases, but in many cases we know how to do it, okay? And what else I want to say about them? So I want to say that if you now consider the whole set of these correlators, what you take your Q to be? So we said, oh, these correlators, this one of these correlators. Or given 15 they are very similar in structure to a CFTP, okay, to a conformal field theory in the dimensions. But again, the properties are conformal covariance to the dimension. So I will have the same amount of the generators of the conformal group. I will not do a review of conformal field theories in this class, but we also don't need a lot of details. Okay, the basic is that we have these symmetries, slash special conformal, rotations and dilatations. Then another thing is that there is an operator product expansion that converges between these boundary operators, use them together, exactly like you would do in a conformal field theory in the dimensions. And this means, as a consequence of the existence of the OP, that we can organize all correlators, or maybe we should say we can, in principle, compute all correlators from a small number of data, small amount of data. Okay.
When you say there's an OPE, you mean there's a finite number of singular terms in the OPE as well, or
There is a, sorry?
finite number of singular, because in principle any QFT does have an OPE. The point with the CFT is that it has a
Well, I mean, it has a kind of a special status in conformal field theory because we have it more under control. We know that it's convergent.
but it's similar here as well.
Here, it's exactly the same status as OP in conformal field theory. I will give some argument why in a second. So we can compute all correlators from a small amount of data, which are.
CFT or is boundary CFT?
I guess you can say in boundary CFT, but it works similar, right? In boundary CFT, the convergence properties are similar to those. Of course, I'm just saying now, if you want, I'm talking about these correlators, assuming that I'm only inserting operators at the boundary. Okay.
And there is no stress tensor.
Exactly. Yeah, I was going to say it in a second. Yes. So these symbols are like the scaling dimensions of the operators and their OP coefficients, which enter one of the products of two primary operators. So again, the finite conformal covariance means that an organized operator is primaries and descendants, and then these OP coefficients enter in the algebra of my primary operators. Okay, and so it's very conceptually nice, as we are familiar from this area of CFT, that we can just characterize this boundary correlated in terms of this data. And there is also crossing symmetry. Okay. And if I'm studying a unitary theory, there are the unitary bounds. Okay, they apply in the same fashion. Because if you think, okay, first maybe I should say we don't have, so what is it we don't have compared to our form of theory in the dimensions in this case? The thing that we don't have, as Andrea already said, is that we don't have locality, meaning that our theory interacts with the bulk, right? And so what is lacking is that there is no stress tensor in the spectrum of boundary operators. Okay, so we don't have a conserved stress tensor, and So you might say, but wait a second, you told me that there are all these symmetries, all these charges, and there is no stress tensor, but usually we get them by integrating the stress tensor. So how could it be? Well, precisely this means that these charges exist, but not as an integral of a current. Okay, so the way this works is that you have your boundary, and there are the isometry charges in the bulk, and the isometry charges end on this boundary. Okay, so I hope the picture is clear. So we have some isometry charge in the bulk, and the end point of this isometry charge works like for this the operator of the hat on my boundary theory. Okay, so using the end point of the isometry, this gives me exactly the same constraints as the dilatation charge.
Could you give an example? Like the translation in the bulk?
Yes, so for instance, suppose the dilatations of the boundary in Poincare coordinates, right, they arise from an isometry in the bulk. So in Poincare coordinates, the vector, the Killing vector of this isometry is something like v dg plus x dx, right? This notation is like I'm using this as two components of the Killing vector, no? Because what does this do? This rescales z, right? And rescales x by the same factor, so it's an isometry. Now, out of this, what we do is always in quantum field theory, in field space or even in flat space, we can build the charges for the isometries. No? And we do this by doing some integral of t0. Now the indices are in a random place.
Sure.
Okay. We contract the stress tensor with the Killing vector and we build a charge. Okay. Now what I'm saying is that if you take this operator, this can end at the boundary. So if you want to be a bit formal, the fact that it can end at the boundary means that my boundary condition preserves the isometry. Okay, you could even entertain the possibility that your boundary condition breaks the isometry, and then the endpoint will not move freely. Okay, but if your boundary condition does preserve the isometry, then this charge can end at the boundary, and it defines for you an analog of the d hat operator. And this d hat now will act like a dilatation charge on all the operators of the boundary. Okay? So you see the integral now is inside the bulk. So on the spatial slice of AdS. Spatial slice of AdS. So in the bulk, I have local charge, I have local currents, not at the boundary. Is it clear more or less the idea? Or should I find more like
can't read the
So here I wrote I wrote that you integrate T0 nu contracted with the Killing vector. You integrate on a spatial slice in AdS. Where we take the spatial, the way we construct charges, usually, we integrate the current on a spatial slice. And now I'm integrating in a spatial slice inside my bulk. Okay? But this will end at the boundary. Okay? So we don't have a substantial, we just have this non-locally realized charges. Questions about this point? I want to expand a little bit on why we have the OP. And the reason is that a very important structural feature of this setup is that we have what we might call a boundary state, boundary operator, bulk state correspondence. What do I mean by that? Again, Poincare coordinates are useful for this. Maybe I should use the color chalk or not. So again, this is the picture in Poincare coordinates. This is Z. Now, what you can do is that usually we think of time as one of the coordinates here, right? If we quantize like this, that was basically the suggestion I was giving there, not the time like that. But we are Euclidean, right? So since we are Euclidean, nobody can stop us from doing a different slicing. So let me take a slicing like this. Okay, so I take my time slices to be some any spheres that are centered at some point at the boundary. You can think of it as the origin of your boundary. Okay, so this is now the time direction. in this kind of quantization. And now think a little bit about this type of Hilbert space that we get here, right? So now you see this is precisely the direction of this isometry that I mentioned here, the one that rescales Poincare coordinates. So this is rescaling in the same way, the z direction and the x direction. And so D gives me time evolution in this quantization. And it's kind of clear that I can prepare a state by inserting an operator at the boundary, right? I can prepare a state in the bulk here by inserting an operator. But thanks to this symmetry, it's also true that vice versa, right? Vice versa, if I prepare a state on one of these slices, then I can evolve it back with my dilatation operator until it becomes just a point at the boundary. So this means that this thing that I wrote here means that if I have a state in the bulk in this quantization, I can always rewrite it as a linear combination of states prepared by boundary operators. Okay. And
Sorry,
yes,
the dilatation is a dilatation in the raw coordinates, right?
no, it's not raw. You're thinking about the
With the sphere.
yes. So in those coordinates, it's always a bit confusing exactly how D acts. But in these coordinates, the dilatation is this one, right? So this is an isometry of the magnetic. Let me write it. So clearly it's invariant under this, no?
Okay.
And these are the, if you want, the slices that I move from one to the other by doing this change, no?
Okay.
Yeah. Now I don't remember exactly how to write the killing vector, this killing vector in these other coordinates, but I can tell you later if you want. Could be that it's just the raw, but probably not. Yeah, because the raw is not an isometry, so I can fix it. Okay. So what I want to say is that now using this, somehow, okay. Okay, I will use this again in a second, but I wanted to stress it, it's important. And so with a bit of a improper language, we call this thing that we have at the boundary, this set of correlators, sometimes we call it boundaries here. Okay. So let me stress there is not some independently defined conformal field theory that exists. It's not the set of all correlators that exist at the boundary of Q AdS. Sometimes we just call it this. Okay. And maybe for those of you that are familiar with the logarithm, I guess many of you are, just some differences. So when we do holography, we have quantum gravity, right, in AdS. So we have also dynamical gravity. In that case, the fact that you have the graviton gives you a stress tensor at the boundary, okay? And in that case, we really think of this boundary CFT as a dual description of the bulk, no? Because like when we do quantum gravity, we have dynamical space-time. There is no local observable inside of our geometry. So all there is to observe, we believe, is what lives at the boundary. Okay? It's an independently defined theory in some cases, we have duality, etc. Here, there is no duality. I'm not discussing any duality. I'm just saying I take a local quantum field theory, putting it on AdS, and there is a subset of the observables, which are these boundary correlators. Okay? So this thing is not really a theory, it's just some observables in a quantum field theory. Okay? But we need to use some common, some easy language, so I call it boundary safety, because saying every time the set of boundary correlation count is a bit boring. Okay. What do I want to say? So let's say a few things about this. So let's do an example. Suppose in the bulk, I start now with the CFT d plus 1. Okay, so this is the bulk theory now. Bulk theory. And I reform it with some relevant operator. Okay, so that's one way we think about defining QFT. Okay, so in the bulk, now I have this CFT deformed by G of. Okay. Now, suppose that this guy has dimension delta in the CFT UV. This starting point. Then you see this coupling G has some dimensions, which is sorry, I forgot to say. What is the dimension of this guy? D plus 1 minus delta. Right? So the idea is plus 1, just by dimensional analysis. Okay, turning on this coupling. And what I want to do is that I will always form in this setup some dimensionless combination. So in this case, the dimensionless combination is going to be G with some power of the radius. Okay. So automatically I get this dimensionless knob. Okay. And now what I want to say is that I don't have really one boundary CFT, but I have a family of them. Okay. Parameterized by this dimensionless coupling constant. So that depending on the value of this dimensionless coupling, the data of the boundary CFT are going to change. So I'm going to have automatically a continuous family of data. Okay. So this is something that those of you who are used to studying conformal field theory, we don't encounter so much in local conformal field theories continuous families of theories, right? It happens very rarely when we have conformal manifolds are called. In this setup, it's like you always get continuous families. Okay, basically, as soon as you remove the stress tensor, you go to this non-local setup. Continuous families are very common. And there is another important difference that this continuous family is not parameterized by an operator of the CFT itself. It's parameterized by an operator in the bulk. Okay, so in changing the coefficient of this bulk operator, I change the data of my CFT. Okay, the boundary. This is nice also because we like to have new dimensionless parameters in physics, right? We can do more calculations. So, for instance, in this setup, you could imagine that you're very strong and you know everything about this theory, perhaps because it's free, right? Now you have your family of boundary CFTs. Parameterized by this G hat, and when G hat is very small, you can do your perturbatively close to the CFT, right? When this parameter is very small, means that AdS is very small compared to my relevant coupling. I can do perturbative calculations using this. And on the other hand, you have the strongly coupled regime is also the flat space limit. Okay. Of course, there is no free lunch. Right? We are interested in flat space. Flat space is going to be strongly coupled from this point of view. Okay. But we gain this new interpolation knob that we can use. Okay. So in principle, here we can do perturbation theory, and then we can try to extrapolate to recover the flat space. Yes.
Can you see this as to make an analogy?
Yes.
And to go a bit slower because I think it's an important part. For instance, when you put the lattice QCD, when you put this with lattice,
Yes.
you usually define the UV action that contains a bad coupling.
Yes.
Then you can study the first order of this bad coupling.
Yes.
In that case, you have like some weak coupling regime, some coupling regime, and is this like a
it's
the same analogy with that the
I think
it's space, and here you have an L.
Exactly. So
They are
okay,
different.
this notion of having a dimensionless knob exists also, as you said, on the lattice. I can do it as a function. I mean, I can normalize all my couplings as a function of the lattice spacing. It also exists if I put my theory on a torus, we mentioned before. Now, the additional point of view that I had here, which I don't have necessarily in these other setups, is that for each value of this knob, I can focus on these asymptotic observables. Okay, so these things I don't have on necessarily on the torus, for instance. Okay, on the lattice, yes, maybe I mean I don't have asymptotic observables. Maybe I care about something else in the setup.
Yeah, no,
But the point that I wanted to stress now was the point of view of the boundary CFT. I wanted to say that the boundary CFT is a continuous family as a function of these dimensionless parameters. Okay?
Each point
yeah.
of samples, you have
Yeah.
the observer interesting thing and like some very definite way which they value with this dimensional scale.
Yes, this way.
This dimensional scale, if you can go to the UV or to the IR.
Exactly.
And also UV IR depends also on.
Mhm. Yes, because typically when you have this relevant deformation, no, what this means is that the physics will change a lot as a function when the energy crosses this scale set by G. No, the G will set a scale in your theory. I lost my chalk. Here it is. Right, so typically the question you want to ask is after you go to this scale, some typical scale set by G, you want to know what happens here. Now I'm saying that using L, you can move the radius of AdS and move your IR cutoff and probe different levels of this RG. Okay, so if you put it very high, which means that this parameter is very small, the RG stops immediately, you can use perturbation theory, and then you can slowly move it and probe more interesting physics. Okay, but the nice thing is that you like can see the data evolving as you. Okay, so it's like you have an evolution of your data at the boundary. Is it clear?
Yeah.
Okay.
Is it clear that you don't generate those fields when you go through the RG? That's because you are infrared safe.
Yeah. So this now it was a cartoon in which I have one relevant coupling, but this, if you want, is a problem of the flat space in a sense, right? So whether you build a verges are going to generate other couplings, and what is the full set of couplings that I need to turn on together? This is a problem that I can solve in flat space because it's a problem of UV, right? So once I solve that problem, now here was one, it could be 12 couplings. I have my 12 couplings, and then I will have 12 parameters that my boundary CFT will depend on. Okay.
So one thing, the G hat that have is undergoes an RG in numerical prediction or not? Or the beta function is 0?
So okay, here, so maybe it was the same question that you asked. So here I was imagining some strongly relevant deformation if you want super normalizable. Okay. So then this was just one number, I don't know, it was 3 TV, and then I measure my radius, I compare it to 3 TV. Now, an interesting thing which we will discuss for your mix, is when you're coupling, it naively looks dimensionless, but then it starts running, okay? So what do you do in that? So this means that this is 0, right? Because it's a classically marginal coupling.
Yes.
So the way you replace that formula in that context is that you will say that your G hat, you can think about it as your classically marginal coupling renormalized at the scale 1 over L. If you want, you can think about it like this. You see? So you stop the G of your marginally relevant coupling, you stop it at this scale. Or another way you can think about it, when you have these classically marginal couplings that then run, you have a dynamically generated scale, right?
Okay.
So you can just form a dimensionless combination of the dynamically generated scale and your radius. It's going to be the same as this then.
But you reflect them.
Yes, yes. You can really use the dynamically generated scale, but we are going to see it for your bills. Okay. Now, let's.
Is there also a way to mathematically study the strong coupling regime in a sense of like adiabatic expansions?
So there are various techniques that you can. So of course, perturbation theory is not going to be unless you are able to compute very a large number of orders and do some extrapolation. We are not there in any case, I know, but you need something to go to do this extrapolation, right? So now what to use depends.
Whenever else starts being a scale, you can expand it.
Yeah, but you can also now think about it just as I have this family of CFTs and I want to study it as this coupling becomes larger, right? Now, techniques that you can use are, for instance, numerical conformal bootstrap. You can hope that maybe you're able to see this family of solutions of the bootstrap equations. That would be one way to go to strong coupling. Another technique, which I will not.
Adiabatic expansion, like
Adiabatic, what do you mean about adiabatic expansion?
like parallel neighbors. Adiabatic expansion.
I'm not familiar with that, sorry. But
The
yeah.
weakest also reference is the expansion of propagators like in recurved spaces. So when you can ask when does the propagator represent the particle propagating, in curve space, or it's just
I don't know. It could be that there are. I mean, I can tell you what people. These techniques I don't know, but I can tell you some things that people have thought of. Is another thing people have tried is to do something called Hamiltonian truncation. So you can take the theory and use some. Basically, write the operator P hat that we were talking about before. You can think about it as a big matrix, then you truncate it and you diagonalize it. Very numerically. So that's one approach that people tried. Seems to be a bit hard in setup, but it has been tried. And recently, people also developed some new techniques which are based on really studying the evolution equations for these objects as a function of this dimensionless parameter. So the group of Job and Adonis, they wrote some differential equations for this data. And that was also promising, but so far it has not been used a lot, but it's kind of
Into D.
into the they did it so far, yes.
Sorry, another
Yes.
question. When you scale G out, you think that you are keeping fixed G.
Yes. Yeah, that's I think it's more or less what I was saying now, that like this G, so if it's strongly relevant, usually we think about it as fixed, right? So if I do a G and I have something which is super normalizable, it's gonna be some scale, and the scale is fixed. So if instead it's something that runs, like classically marginal stuff, then the way you think about this dimensionless number is the things that run renormalize at the scale of the radius of AdS. That's how I'm thinking about it. Does that make sense?
Yeah.
So in that sense,
But then you need probably some other you need some matching condition then to
I mean,
know how you flow.
this thing you might complain that it's a bit scheme dependent, but yes, I mean, I never promise that the value of this G is going to be super independently defined from any convention, but it is a well-defined thing, not to take G a mix in MS bar and compute it at 1 over L. So that's a valid parameter that we use to parameterize the family. Okay. Now, I don't know why I think even now I want to tell you an important consequence of this. An important consequence of this is that there is something called boundary operator expansion. I was hoping to get 2 minutes at the end of this first class. Let's see if I manage. So something called boundary operator expansion. So this boundary operator expansion. We shorten BOE. What is the idea? The idea is that in this series, suppose I have an insertion of a bar operator at some point, then I can surround it with one of these spheres. Okay, I can surround it with one of these spheres, and now this is going to prepare a state for me on the slice, right? So this evolution is Euclidean time. I'm going to prepare a state here, and then I can evolve it back. And what this means is that the insertion of the bulk operator can be rephrased as a sum over infinitely many insertions of boundary operators. Okay? Because we said before that these states can be seen as a superposition of boundary operators. So the way what this produces for you is some expansion of this form, and some over. Sometimes to distinguish boundary operators, we put hats. I will not be super consistent with this, but in this equation I will put to distinguish. So these are boundary primaries. And we have some coefficients here times some power of z. And then you will insert the boundary operator at the point x. You see this is some z and some x. And then there is an infinite sum also over descendants. Descendants just means like derivatives acting on O. Okay, so there's going to be an infinite sum over descendants, but this full sum over descendant is completely fixed by the symmetry. Okay, so it's boring in a sense, it's fixed by the symmetry of the problem. The only shifting bit is these coefficients. So these are called DOE coefficients. Well, for those of you who know boundary conformal field theory, it is all the same as boundary conformal field theory, but it works also in this case, okay? So compared to boundary conformal field theory, the only thing that we miss is that we don't have OP in the bulk. We don't have a convergent OP in the bulk, okay? This was a comment for experts of BCFT. And so, yeah, so in principle, I can add this bit to my data if I want to have also correlation functions in the bulk. Then I will the full set of data of my theory are going to be these dimensions, these OP coefficients, and I also have these POE coefficients. They will also depend on G hat. And this is what the group of Joachim and Noyes proposed to call the QFT data. Okay? In the sense that in terms of this stuff, I can express any correlation function now of my theory, also the bulk ones. Perhaps now, the last 10 minutes, I want to give you a simple example. Okay, so it's something that you all know because you studied the DSCT probably in some capacity. So, but we want to, I want to just reinterpret it in this language just to warm up with it. And it's an example of the free scalar, free massive scalar in AdS. So let me do that. Let's start here. But okay, maybe I should ask first if there are questions. So this was a bit more a bit abstract. Now let's try to make it concrete with this example. So simplest example perhaps of this graph is a free scalar. Okay. So what is the action? We just have our action is ds2 plus 1. There is an integral of sorry, it is potential, right direction of the free scalar. Median. Okay. So let's use our sophisticated approach for this simple case. So what do? We see this action, we say, this is a CFT plus a relevant operator, right? The mass. So this means that we have a dimensionless parameter, which is the combination of this with the radius of AdS. Now, this dimensionless parameter should parameterize a continuous family of boundary CFT. Okay. But here we are going to see something that I forgot to mention, which is in this example now we see it explicitly that actually specifying these bulk couplings doesn't uniquely fix the boundary behavior. What is yet to be added is that there could be some usually discrete set of choices, okay? And these are basically choices of boundary conditions. So even if you completely fix your boundary theory, your bulk theory, you fix the couplings, it's not like guaranteed that there is one continuous family of boundary correlators. It could be multiple continuous families. These multiple continuous families correspond to different choices of boundary conditions. Okay, so let's see in this example. So now the next question we ask in this example is, what are the boundary conditions?
Lorenzo, we can go a bit over time. There is no rush.
Okay, okay. But maybe, yeah, it would be nice if at least I finish this example.
No problem.
Then tomorrow we are going to use the same philosophy for it.
Yeah, you consider until 12, because I consider some 10 minutes for questions, so you can go on. Until
Okay.
12.
Thank you. So now, if you consider, so how do we fix the boundary conditions? in these three examples, in the examples in which we can rely on our action, the requirement is that the stationarity of the action on the equations of motion, right? So what do? We take our variation of the action, we impose the equations of motion. Now, this we are familiar that now we derive the equations of motion from the minimum distraction principle. So if we evaluate here, the back term is going to go to 0. Okay, so this cancels the back variation. But typically you're left with some with some boundary term. So you need to impose that this is 0. Okay, so there is a boundary term coming from here, and you need to set it to 0. Now, so you basically have two requirements at once. So your solution needs to satisfy the equations of motion, and it needs to set to 0 this boundary term. Now, if you do it in the case of the scalar, you just have the high-Gordon equation. Okay, and what you discover is that the boundary behavior, it has this form compatibly with the back equation of motion. Okay, this is just a coefficient. Okay, so this is the leading boundary asymptotics of your field, where this power delta satisfies this differential, this algebraic equation. Okay, so this comes from Gordon. Okay. For some reason, I didn't write it down, but if you want, you can ask me about the derivation. But you just get this constraint. Okay. Now, and this you can also check that it satisfies the fact that this goes to 0, like this power of z, will also satisfy that the boundary term vanishes. There is a little bit of a caveat, if you want, that you need to be careful that when the delta is smaller than the other two, you need to add a boundary term. Okay, so this I will not tell you the reasons because it's also important. But this thing satisfies both constraints at the same time. It satisfies the equations of motion and it sets to 0 the boundary term. Now, let's reinterpret this boundary condition. Now, let's see what it tells us from the language that we were using before. Okay, so in the language that we were using before, what happens is now this coefficient O, it behaves like an operator in our boundary of the theory, so we can insert it and compute correlation functions. So the boundary Smithy now contains an operator O, which is of spin 0 and scaling dimension delta. So this delta, the power that appears in the boundary behavior, is a scaling dimension. Okay, this you can easily check because under the isometry this is a scalar, right? So if you rescale both z and x, you need to get z rescales, x rescales, and this needs to soak up the power of z. So it means that it's an operator of dimension delta. And since our theory is Gaussian, it means that all the correlation functions of this O can just be computed with contractions. Okay, so it's a very simple. It's a very simple set of correlation functions. All boundary correlators are computed by weak contractions. So it means that one is a simple function. For instance, we will just do all possible weak contractions, where one single weak contraction is okay, it could be some normalization. It's just given by the usual power law about my function. And this type of theory, in which all the correlation functions are computed by weak contraction, is what is called generalized sum theory. Okay. And it's also hard to prove that all the spectrum of operators then is going to be just products of O and its derivative at the same point. Okay, so we can just write all boundary operators. All boundary operators in this case, just stuff like O squared, O with some derivative inside O, and then they're going to be operators with 3 O's, okay, and so on and so forth. They're all products of this operator O, and the dimensions are additive. So for instance, if you want to compute
That's sufficient to prove that generalized Greek theory has a Fox space local operation.
well, yeah, so this I think it's a nice way to think about generalized free theory. One way you can think about it is that it's the free theory inside of the zip, okay? So yes, you can write, if you want, you can rewrite this field in a more standard way of quantizing free theories in terms of the identity of the Fox space and all that.
That's what I'm saying.
Yes,
And then here it's obvious that one can construct
Exactly.
Fox space. Is
Exactly. So you can reinterpret everything you do usually in generalized free theory, you can reinterpret in terms of the box space of this field entity.
yeah, but my question is it derivable from the simple fact that correlated pairs are weak contractions?
I mean, depends exactly what you want to derive, but one thing that is definitely true is that you can think of the number of operators that you have here is associated to the number of particles. Okay, so in a sense, states associated to this operator are going to be 2 particle states. These are going to be 3 particle states, and so on and so forth. Okay, so you have this structure which is organized in number of things. You can either think of number of operators, number of O's you have in your operator, or you can think in terms of number of particles in your Fock space, because things are very closely related. And so yes, what I want to say that the dimensions are additive. So for instance, if you have an operator like this is going to be dimension 2 delta coming from 2 O's plus 2 by the derivative. Okay. And so let me conclude by now doing a plot of the family of CFTs as a function of the dimensionless parameter m squared. So where do I do it? I do it here, right? So the ring of space. So let's draw now the continuous family of CFTs as a function of this guy. So one point here is that you see that all the correlators are basically fixed in terms of this parameter delta, right? Because I told you that all the correlation functions are just computed by weak contractions. All the operators are they just have additive dimensions. So once you give me delta, I can compute all the data of this boundary theory. So if I want to parameterize my boundary theory, I can just use delta. Okay. So the plot I'm going to do is just a plot of this relation we saw before. Okay, it's pretty innocuous, but we see that there is some interesting features. Let me just do a plot of this. This is a parabola. So I want to draw with some colors. So let's say that this is D. D over 2, 0, represents kind of. So draw 2 branches. And I should also single out here some value, which is e over 2 minus 1. Okay. So when delta is below d over 2 minus 1, we are below the unitarity bound in a conformal field theory in the dimension. So it means that the theory is not compatible with unitarity. So this whole part of the solution we should cut out our diagram. Okay, in the sense that it's non-unitary. Now here we have a very small region, right? But we actually have 2 choices. And a comment here, you see m squared that I also considering negative values. This is the famous fact that in anti-de-Sitter, we keep having a stable field theory from the scalar, even if this m squared is negative, as long as it's above the minimal value, which is called the Berthelon-Friedman bound. Okay, so this is here is the Berthelon-Friedman bound. And it turns out that this window, in which this small window in which we have two choices, is between m squared Berthelon-Friedman, and it's the same mass plus 1. Okay, so this small range of masses, we have two choices. And so let me call these two choices plus and minus. I'm almost done. This is plus. Here the dimension is bigger than the other two. And this other branch is minus. And the other solution is smaller than the other two. And some interesting features. Let me write here some interesting features of this plot. Is the plot more or less clear? It's like just a parabola, okay? Maybe I should have done a little bit bigger, the interesting part. Okay, so it is. You have a question about the plot?
Yeah, because there are too many lines cancelled and then got.
So this region I wanted to cancel because it's below unitarity bound. You see, so this is the other two, this is the other two minus 1. So when delta is smaller than the other two minus 1, unitarity forbids you to consider that boundary condition. Okay?
Okay.
So there is a very small region between these two values of the mass, the Bernoulli-Friedman bound and the Bernoulli-Friedman bound plus 1, in which you have two choices. You can choose either the blue or the red, or both are valid. Does it make sense? Yes?
So unitarity for the boundary safety is the same between unitarity.
Yes, yes, because how do we prove unitarity? No, we start with the state of the primary, and then we act on it with some t's, and then we require that the norm of this is positive, right? And this gives us the delta must be bigger than this value. But this I can do exactly the same. I have the state associated to this operator because I have the state operator correspondence. I have this p. Okay, it comes from the bulk in some subtle way, but it still exists. Okay. So if I require the norm of this to be positive, I get the same bound. Sorry, I'm not convinced by my Lorenzo.
I don't know, I'm confused, sorry.
No, but I'm just saying that. But maybe I will have a confusion. And let's see if you don't. If some of the things I'm saying is confusing, you can. Just to say also that here there is a flat space limit, right? Flat space is here because this one is big. So what are the features that I want to stress? One thing that I want to stress is that for a sufficiently large radius, I have only one option for the BCs. Only one BC is unitary. This is kind of reassuring because I was claiming before that the large radius should give me S matrices in flat space. But usually when we compute S matrices, maybe we should, but typically we don't start discussing what are the boundary conditions at infinity. So it's reassuring that here I have only one option that survives indefinitely, right? Another thing is that, because of course, let's look at this plot from moving from flat space and going inside. Okay, so here I'm in flat space, I have one boundary condition that gives me my S matrix. Then I start moving. At some point, I arrive here at this value, Bernoulli-Friedman bound plus 1. Okay, this is the value Bernoulli-Friedman bound plus 1. And here something weird happens that I get this additional thing. So before, this was a non-unitary boundary condition that existed, and all of a sudden this unitary boundary condition pops out into existence and it becomes unitary. Okay. The boundary condition, the BC minus emerges as a unitary option. Okay, before it was what is called in some terminology real non-unitary. What does it mean real non-unitary? there are various degrees of things that are non-unitary. So there is only one way to be unitary. There are many ways to be non-unitary. So this thing was non-unitary, but all the observables are real. Like it's just that they are below unitarity bounds. Okay. Then okay, magically this thing pops up, and then the two of them at some point, when I reach the Bernard-Freeman bound, they merge. For m squared equal the Bernard-Freeman bound, this negative m squared is the minimal value allowed, plus and minus undergo what is called merger and annihilation. What does that mean? You see, if I try to continue below this point, it's like these two solutions become complex. They stop existing and they become complex. So they are not allowed anymore as boundary conditions for my system. So this is interpreted as an instability. This is very clearly an instability, right? Because I'm making the mass too negative. If I make the mass too negative, there is an instability in my system.
Sorry,
Yes.
that's what was confusing that why the theory in the bulk is sick?
The theory in the bulk
Is sick. Why it's sick?
it's sick because the mass square is too negative, right? I mean, actually, it's less sick than you would expect. I'm telling you that you can even consider this potential and AdS is happy, but you cannot exaggerate, right? If you take it too negative, then at some point it's not happy anymore. You see what I'm saying? I mean, this is the potential. So at free scalar, usually we don't consider negative mass square. Okay?
Oh, no, that's fine.
I'm just saying that if you take it too negative, there is going to be an instability. But I want to tell you something more about how the instability manifests itself from the point of view of the boundary, right? So I have this beautiful boundary condition. Then when I take the mass to negative, at some point, this new thing, this new boundary condition pops out, its own existence, and then they merge.
So if you carry the bound, the mass is zero. That's what you are saying.
No, sorry,
The mass is zero. So if you
the mass, sorry, this is the zero mass. So there is this range where the mass is negative. So let me zoom in. I did it too small, the interesting part of the plot. Let me zoom it in. So the interesting part of the plot is this. Well, this is 0 and for the no, should be smaller here. And here with this, okay. Here's my parabola. So this is 0 mass, and 0 mass is dimension d, okay. So this is d over 2, okay. Then there is somewhere here d over 2 minus 1, okay. And when d over 2 minus 1 meets, let's see, let me try it a little bit lower. D over 2 minus 1.
what about if we can D? So that you know things.
It's not, it doesn't change anything. Okay, so you see, this part doesn't exist because it's below unitarity. You see? This is all negative mass squared, this part of the parabola. Positive mass squared is only this branch. So this is positive mass squared. I only have a plus boundary condition, nobody does that. Also for this part, which is negative mass squared, I still have only the plus boundary condition exists. Plus means that the dimension is bigger than the other two. And then there is this interesting part between the two values, which are Bernoulli-Friedman and Bernoulli-Friedman plus 1. Okay, between these two, Bernoulli-Friedman, by the way, is minus x squared over 4. Okay, so this is minus x squared over 4, this is minus x squared over 4 plus 1. In this region, I can choose both the minus or the plus. And what I wanted to stress is how the instability, so there must be an instability here because you cannot take the mass square to negative. Yes. The way the instability instantiates, I don't know how to say, the way that happens is that at some point the new boundary condition comes out, this minus, you lower the mass, at some point you get this new boundary condition, and then the two of them merge and annihilate. So that's the language I want to use to describe what is happening. Does it make sense or?
Yeah.
Can one also think in terms of taking the normal to the limit where AdS becomes a harmonic potential, then the energies are just a mass times d/2. And we're just requiring it to be positive, right?
You mean to get this better optimal bound?
No, to understand the stability. I'm trying to think what can
Well-
understand the stability from the point of normal to this take the limit of AdS. It's just a requirement that the energy is be
I didn't derive for you that the stability, but the physics of the stability, the way I prefer to think about it, there are many ways to think about it, but the way I prefer to think about it is just the Euclidean function is something like this. And you want this thing to be positive,
Yes.
right? Because otherwise it's not damped, you're at the integral. So this minus this square over 4 is just the lowest stable value of this guy. You see? So if you take the mass squared smaller than the lowest stable value of this guy, then instead of having an exponential convergence in your filter, it will diverge. Okay, I think I can conclude here, and then tomorrow I want to draw similar pictures for your mates.
Let's thank Lorenzo. Okay, now we have the break. We go all together to room seminar 3.2 where we have this lunch coffee break.
leave our stuff.
So good. Now we can leave our stuff here. I will just bring you to this seminar 3.2. Then I will come back and close the okay. And then we meet again after 2.